nanohub.org. It really set the basis for compositional contrast using atomic force microscopy when you use tapping mode images, right? And so the key conclusions from the lecture last time were the notion that every cantilever has multiple eigenmodes, right? And these happen at certain discrete frequencies. You choose to drive the cantilever at one of those chosen frequencies, and the cantilever vibrates in a characteristic shape. Each peak you choose has its own equivalent stiffness depending on the shape of the deformation, the strain energy, and the eigenmode, and so on. And we talked about how you can try to figure out what's the equivalent stiffness of that mode. The good news is, even though it's complicated, there are many eigenmodes. Once you choose a certain peak for operation, you can represent it by a point mass model with the appropriate spring constant, and everything's okay. Now, with that in mind, we went ahead and started developing a analytical framework for understanding what is phase contrast in tapping mode AFM, what it means. And we talked about the fact that it's very important to make a distinction between phase lag and phase lead in your AFM systems. Has anyone of you had a chance to look at your AFM system to see if it plots phase lag or phase lead? Yeah? And? So you did, yes, of course. And it's phase lag, right? Okay. Not easy to figure out. I mean, you have to do this tuning curve and really sort it out pretty well. It's not easy. It's tricky. And if you don't do it, you don't know what you're seeing. You don't know what dark and bright spots mean in an image, right? Something so important. The key result was that there are two quantities that actually the phase is divided into sine of phase lag and cosine of phase lag, where phi is the phase lag. The sine of phase lag is connected to energy dissipation per cycle. As the tip comes and cycles and interacts with the sample, there's some net energy loss, which is related to sine of phase lag. And then there's another quantity related to cosine of phase lag, which is this quantity that we call the varial. Okay? We'll talk a little bit about, again, reminding you all what it really means, okay? Any questions on what we did last time? The mathematics should be pretty clear. It's simply trigonometry. You multiply by sines and cosines and do the integrals over the time period. The underlying assumption in the theory was the tip oscillates sinusoidally. That's all, harmonically. So that was the key thing. Yes, Hank?
Good question.
Yeah.
So let's say you had a processing software,
yeah,
and you wanted to solve for the varial, per se. And you have FTS times the displacement. But in your images, you might not know FTS per se.
Well, so what you would do is, if you want to plot the varial, what you do is this. You plot cosine of phase lag times stiffness. I mean, the observable is the phase lag and the amplitude and the Q and the K. So you would use...
For is FTS times S.
Right.
Okay, I see. Thank you.
Just the same way as what you're doing with the first equation, you're solving for E dissipation, E dis. Right? So those are two important things. Yeah, so the key thing is, from what you observe in a tapping mode experiment, you can get numbers in terms of what's the energy dissipation each time the tip comes and interacts with the sample in picojoules or electron volts. It's amazing. If you have a chance, you should try to apply these formulas to convert your phase to energy dissipation. It's really, really worth looking at the numbers you get. And the cosine of phi is related to the varial, as we talked about last time. So let's go back and again look over what the physical meaning of energy dissipation and the varial are. In our analysis, we assume the tip motion x of t takes the form a cosine omega t minus phi, where omega is the drive frequency, the frequency at which you're shaking it, which of course is going to be close to the natural frequency omega 0, if not exactly equal, because you want it to vibrate at resonance, right? So resonance happens when omega equals omega 0. All right. Phi is the phase lag. That's why it's minus phi up there. All right. So what this means is the tip is oscillating, as shown in the blue curve, x of t, right? So x of t is this a cosine omega t minus phi. That's the blue curve on the top graph. Everyone okay with that? That's the blue curve in the top graph, okay? the x-axis here is actually not time, but omega t minus phi. Okay? So when omega t minus phi is 0, you're at the very top, which is what I've shown there. So it's a cosine, basically, of omega t minus phi. Okay? So the blue curve on top is simply cosine of omega t minus phi. All right? Now, that's how the tip is moving. And when x becomes negative and goes down is when it's approaching the sample, right? So what you're looking at is this motion, up and down, right? So what's going to happen is, while that's going on, you can also plot in green on the top graph what the velocity of the tip is doing. If you assume the tip displacement is a cosine omega t minus phi, the tip velocity is going to be negative a omega sine omega t minus phi, okay? Which is plotted in green, right? Which basically says that when omega t minus phi is 0, when the tip is on the very top position, the velocity is 0. As it starts approaching the sample, the velocity becomes more and more negative. Negative velocity means you're approaching the sample. Until you reach the bottom of the swing. When you're at the bottom of the swing, the velocity again becomes 0. And then as it starts swinging up from the bottom, the velocity goes up, becomes positive. Okay, so the green on the top is the assumed velocity profile of the tip as it's interacting with the sample, okay? Now, what's going to happen in a tapping mode experiment is most of the tip-sample interaction is going to happen at the bottom part of the swing of the cantilever, because for the most part, your oscillation amplitude might be 10 nanometers, 20 nanometers, but your tip-sample interactions, the forces, are going to occur typically in the first 2, 3, 4, 5 nanometers, okay? So what is happening is, when you do tapping mode, for the most part, the tip is not experiencing the interaction forces. It experiences the interaction forces only at the bottom of the wave form, right? When it comes close vicinity of the sample. So in this case, I have placed the sample at that solid horizontal line from which the D is the tip sample gap. The origin of D equal to 0 is shown there, that's solid. So which means that when D becomes negative is when you're indenting the sample. When D is positive, you're above the sample. So roughly, interaction forces will exist in a range of time period where the tip comes close to the sample or indents with the sample and so on, okay? Now, let us take a look at, if this is the situation, let us take a look at what is the history of tip-sample interaction force. Okay, so in other words, in the graph below, now we're plotting the tip-sample interaction force. As the tip goes up and down like this, what forces is the tip feeling as it moves in time, okay? Let us assume first that the interaction force is conservative. Now, all of you know what a conservative interaction force means. It's a force where the tip sample force depends only on the position of the tip, not on the velocity, okay? Now, if the position of the tip is changing as shown by the blue graph, the sine wave shown on top, I hope you'll agree with me that the interaction force we're going to feel, the conservative interaction force, is going to follow a profile shown as blue in the graph below. Okay? Let me explain what's going on. At first, when the tip is approaching the sample, it's swinging low. You're coming down along the harmonic on the top. You're coming below. At first, you're going to experience an attractive force, right? Because the tip is approaching the sample, you have van der Waals forces. You're experiencing an attractive force. So as you move forward and march forward in time, the interaction force experienced by the tip, shown in blue in the graph below, starts to dip. It means it becomes more negative as you're approaching. That means more and more van der Waals forces until you contact. And as you contact, the interaction force starts slowly becoming repulsive. So the blue curve starts pointing up and going up, right? And you indent up to a certain point, and then you move away because it's a harmonic motion, right? As you move away, you follow the blue curve on the right-hand side, which shows the repulsive force decreases, and then you release from the surface, and you have van der Waals force, and you move further away, and there's no force anymore when you move further away from the sample. So the blue is what you would get if you had only conservative forces, attractive and repulsive. The most important thing is, please keep in mind, the blue curve, the history of conservative interaction force, is symmetric with respect to the center line shown there. Why? Because the motion you're assuming is harmonic, so it comes in and moves away at the same rate. And the interaction force, conservative interaction force, only depends on the position of the tip. So whether you're approaching or moving away, it should give you the same answer for the same position. Everyone with me on that? This is a very important thing. So as you move forward in time, the position of the tip moves in, moves away, but as it moves in, moves away, at every instant of time, wherever, for the same position, whether it's approaching or moving away, it should experience the same conservative force, if it's a conservative force, okay? Conservative forces are van der Waals forces, elasticity, and so on. Electrostatics also. So, very important point that if the interaction forces are conservative, the history of tip-sample interaction force, this little interesting pulse that you see, is going to be symmetric about the center. Whether you move in or move away, the value of the force is going to be identical. Okay? Everyone with me? On the other hand, you can have dissipative interactions between the tip and the sample as you're tapping, and there are a multitude of reasons for it. We've talked about this in the past. You could have viscoelasticity of the sample. You could have anelastic processes as you're punching the sample and moving away. Maybe you've caused dislocations and, you're inducing defects in the crystal as you move away or you could have situations where as you touch, you've created some bonds, you move away, you're breaking some bonds. So any sort of irreversible process that now depends on the velocity. Whether you're moving in or moving away, you have different forces now. Okay? So these are now velocity-dependent forces. If that happens, those forces will be something like what's shown in green. Why? Because they will depend on the direction, on the velocity. So you see, if you look up at the green curve on the top, the velocity is changing directions. You see that? At the bottom, the velocity changes directions. Therefore, if you have a dissipative interaction force, it must also change directions because it depends on velocity. Okay? Which means a generic shape for the dissipative interactions is going to be as shown in green, which means it's going to be antisymmetric with respect to the center, because as you approach a sample, the velocity is a certain direction. As you move away, velocity is the opposite direction, right? So it has to be antisymmetric. When you move in, move away, the directions of dissipative forces have to change. If they don't change, then it's a conservative force, okay? Very important. Which means that in reality, if you assume that the tip-sample interaction force consists of dissipative and conservative components, in reality, during one oscillation cycle, the interaction force is going to be as shown by the dotted line here. It's the sum of the two, right? So you can see that the history of tip-sample interaction force during an oscillation cycle consists of a symmetric part and an asymmetric part superposed on each other. So it's kind of slightly skewed. The extent of skewness tells you the amount of dissipative interactions. If it's perfectly symmetric, then it's only conservative actions. Okay? Very important. All right. So now let's go back to, in the light of this graph, let's try to understand what we derived last time. We derived an expression for energy dissipated during one cycle of oscillation in tapping mode AFM, and how you can get that number in picojoules or in electron volts simply by knowing what the phase lag is and knowing what the spring constant is and the Q factor is and the amplitude is. Very simple, very important relationship. Ultimately, what it is the integral over the oscillation time period of the tip velocity times the tip sample interaction force, okay? Now, the tip velocity is given by this A omega sine omega t minus phi, okay? Now, what I want you to realize is that it's tip velocity times the tip sample interaction force, but because the tip velocity is sine omega t minus phi, it only picks out, in this integral, remember, FTS consists of dissipative and conservative interactions, right? But keep in mind, conservative interactions are symmetric with respect to the center, right? Dissipative are asymmetric with respect to the center. So this term, sine omega t minus phi, if you look at it, is asymmetric with respect to the center, the bottom point. You see that? The green curve on top is asymmetric about that dotted line. So when you multiply a symmetric and an antisymmetric function, integrate over a time period, you get 0. On the other hand, you take an antisymmetric function, multiply with an antisymmetric function, then you get a non-zero integral, all right? So what happens in the energy dissipation term is, when you're multiplying the tip velocity with the tip sample interaction force, that product, when you integrate it, does not contain any conservative interaction force, because conservative interaction forces are going to be symmetric about the bottom position. As a result, what you get is simply the dissipative component of the force inside the integral, all right? Which is why the E dis is simply A sine omega t times the dissipative interaction. That's why it's the dissipative interaction. The second term is the varial. The varial that we defined last time is the following quantity, is the integral over the time period of the tip position times the force it experiences. Okay? As simple as that. Again, the tip position is given by the blue curve, it's cosine omega t. So the tip position as a function of time is symmetric with respect to the bottom. So when you multiply it with respect to the interaction force, you've got a symmetric function multiplied by the product. The only product that survives the integral as non-zero is when you multiply it with a symmetric part, symmetric with symmetric. And so what you're left with is just the conservative interaction forces, which is why the varial gives you information only about the conservative interaction forces. So what does the varial mean? The varial is basically saying, as this tip is oscillating over the oscillation cycle, I'm going to record the tip sample interaction force at every time instant. But I'm not looking at average interaction force. Rather, what I'm doing is, at every instant of time, I record the position of the tip, I record the force it experiences, and I record the position times the force during the entire oscillation cycle, and that's what is the varial. So it is not the same as the average interaction force. It's sort of weighted by the position. In other words, forces that occur on the tip when the tip has moved at its extreme position are weighted more than forces when it's in the middle of the oscillation. Okay, so it's a sort of a weighted moment, if you will, of conservative interaction forces. Okay. It's not the average. It's some sort of a moment of the distribution. All right. So the last time we derived these very two important results shown here, that the energy dissipation is connected to sine of phase lag, and this term is really the time average of the varial is connected to the cosine of the phase lag. Okay, very important quantity. So when you have phase lag, if you actually split it into sine of phase lag and cosine of phase lag, you get two independent properties out of it, and you can really map changes in conservative interactions or dissipative interactions over the samples just from one number, phi. This is a very important issue because I think there is probably no paper out there that makes a distinction between sine of phase and cosine of phase. Everybody, when they talk of phase contrast, they just, first of all, I already showed you, most people don't even care or bother to say if it's phase lag or phase lead, which is so essential. You know, if you get a bright or a dark, surface, how do you know which is more dissipation, less dissipation? That's one. Secondly, they don't even make the distinction between plotting sine of phase and cosine of phase. Just because you get, if you want to do some quantitative understanding of if dark spots mean double dissipation compared to another area, if you want to know those kind of things, you got to plot sine of phase and cosine of phase, okay, separately. Very important. Nobody does it. So if you start doing it, we can start this movement to have, to use, let's say, the duality of phase. It's a dual nature of phase, right? You get both information out of it. So let's make a compact here, and all of you, when you take phase images, now let's do sine and cosine, and let this be the Purdue school of thought. Duality of phase. Okay, so we can now move forward to talking about a couple of other important results using analytical approaches. See, what we're now doing is analytical approaches. You can do Veda, but at the end of the day, it's nice to have simple relations analytically that help us understand what's happening. So this is an important result which is very relevant also to when you do frequency modulated AFM. So this was originally derived by Lug and Wang back in 1998, but it basically uses the same thing. It's the same derivation we did last time, but just the grouping of the terms is slightly different, that's all, okay? And the question that's asked is this. It's a very simple question, okay? So when you drive a cantilever to resonance, you bring it close to the sample. The question is, why does the amplitude decrease? Now, to all of us, it's like, of course, the amplitude is going to decrease. Why is it not going to decrease? Because it's interacting with the sample. But you ask the fundamental physics question, and you find, again, there are all kinds of mixed answers in the literature. Some people say, oh, as you interact with the sample, it's the dissipative interactions that reduce, that there's more damping somehow. As you're tapping on the sample, there's more dissipation, and that reduces the amplitude because you're taking energy away. Right? That's one group of answers. Another group of answers is, no, it's not dissipation. It's because of the conservative interactions. They cause force gradients. Force gradients cause shifts in frequencies. If the frequency shifts, you're keeping a fixed frequency, so the amplitude, you're getting off resonance, the amplitude decreases. Which is right. I'm telling you, for the longest time, people did not really understand. And so you found the words damping and frequency shift used simultaneous to explain the reduction of amplitude. Why does amplitude? Well, some papers will write, it's just that there's more dissipative forces, the cantilever, the oscillation gets more damped. There are some people who say, no, it's the conservative force gradients that shift the frequency. So it's a very basic question because at the end of the day, why is it important? Because I think you need to understand very well what does an image mean in tapping mode. What is an image, right? After all, what we do in tapping mode is keep amplitude constant. So it's important to understand that in the process of keeping amplitude constant, what is the fundamental physical quantity that we are keeping constant over the sample? Is it the tip sample force gradient, i.e. is the topography you get in AFM, tapping mode AFM, is it basically a contour of constant force gradient over the sample? Or is it a contour of constant dissipation over a sample? What is it? So we're asking now a very fundamental question. You get an image, but fundamentally in terms of forces, what is it? Is it that by keeping amplitude constant, are you keeping the force gradients constant or what, right? This is an important question. So this is what this paper tried to address. The mathematics is in fact identical to what we did last time. So let's go over this really quickly. The equation of motion for a point mass oscillator model is shown on top. Same as yesterday, or the last class. We're going to assume that x of t, the tip motion, is a cosine omega t minus phi. Phi is the phase lag. X dot, the tip velocity, is then given by negative a omega sine omega t minus phi in equation 1. Plug these things into the equation of motion at the top, and you get equation 2. You multiply that whole equation by sine omega t minus phi and integrate over the time period. And you get exactly the equation 3 that's shown out there, okay? Where the term in the integral, sine omega t minus phi times FTS, I hope you now see, is related to the energy dissipation, because it's basically velocity times the interaction force. It's the same thing. Except now in Lugan Wang's analysis, what you would do is, you would take this entire term on the right-hand side, which is, remember, it's omega over omega 0 q plus this integral term. Let's lump that all together and call it omega over omega 0 times q effective. Okay? So what this means is, it's a way of saying that, q tells you, what is q? Q tells you the q factor of resonance, right? When you do a tuning curve, how sharp it is. That q, if you think about it, is fundamentally a measure of how the energy of oscillation is dissipated in the surrounding medium, into hydrodynamics, into viscous drag in the surrounding. This other term in the integral is connected to energy dissipation at the tip sample interface. Okay? So the first term is dissipation as the whole cantilever oscillates in a viscous fluid. The second term in the integral is telling you about additional dissipation when the tip collides and moves away from the sample. Okay? So what Lugan Wang did here is he said, let's put the whole thing together. Dissipation is dissipation. Let's not worry about the source of the dissipation. Let's lump everything together into a Q effective, right, in the bottom. So you equate the sum of these two to omega over omega 0 times Q effective, where Q effective is now a number that includes in it dissipation due to the standard Q plus the E dis term from the previous analysis. Okay, where 1 over Q effective is given by this, okay? So Q effective now includes dissipation due to both effects, the tip sample interaction and due to viscous hydrodynamics of the cantilever. Equation 4, what you do is you take the same equation of motion multiplied by cosine omega t minus phi like we did last time, and again, you get an expression that's related to the varial now, except what again is done in Wang's paper is he clumps everything together and says, well, let's replace the first term in equation 4 on the right-hand side by some omega effective squared, where omega effective squared is simply given as 1 minus this entire term out here, okay? So what they're saying now is, in this case, they're saying that let us say that the tip sample interaction forces are somehow changing the effective natural frequency of the cantilever also. So it's a grouping of terms. Let's call this omega F effective now. But now you have to keep in mind that this omega effective depends on the interaction forces, right? It depends on what the properties are of the sample, okay? Both things. So when you combine the two things, equations 3 and 4 together, you get a very nice expression for what is the amplitude, steady state amplitude, in terms of omegas and so on. So this expression, the reason it's nice is, if you go back a few lectures and we did the transfer function of a cantilever driven by a force, right? Simple harmonic oscillator, what the transfer function is, what the amplitude and phase is, it takes the same form. This is the same form as a standard transfer function of a cantilever that's forced. And if you want to know how its amplitude changes with drive frequency, this is the same expression, except in the denominator, you've got omega effective and Q effective now, which include in it tip sample interaction forces. Omega effective includes conservative interaction forces because it has a varial in it. Q effective includes the E dis term. So what this expression shows is that when you're far from a sample, when there's no interaction, omega effective is going to be equal to 1. So when there's no interaction force, omega effective is basically 1. And Q effective is going to be Q, right? So when you're far from a sample, you have certain amplitude A0. When you come close to the sample, omega effective starts changing because your varial, you start interacting with the sample and there's a varial, non-zero varial associated with it. There's a non-zero, and the Q effective starts changing due to the tip sample dissipation. And so the amplitude A now reduces because the denominator is increasing. Omega effective, Q effective are changing. And so the amplitude decreases. So this is a very nice result, which basically shows that when you look at amplitude reduction, it's caused by both tip sample dissipation and by tip sample conservative forces. What this means, therefore, is when you scan over a sample with a constant amplitude, you're not, in fact, the image you generate is, in fact, not a contour of constant force gradient. It is a contour that mixes tip sample dissipation and conservative force gradients. It's a very fundamental thing we're talking about here, okay? So, very important result. Deep result, actually, so. Okay. Right, so this is the key point. All right, so one more very important analytical result to do is that of average force, okay? So what we are looking at here now is, oh, this is great. You know, we have an idea of what phase means, but it's force microscopy and you're tapping on a sample. You always want to know how hard you're tapping on a sample, right? Because if you have, you want to be sure, because, you know, when you do static FZ curves, you know exactly what force you're applying, right? When you do tapping, unfortunately, you don't know what force you're applying, because all you know is the amplitude and the phase. What you don't know is, are you applying 10 nanonewtons? Are you applying 20 nanonewtons? By the way, when I say 10 nanonewtons in AFM is already a large force, do you know why I say that? 10 nanonewtons is a large force already? The pressure is extremely large. So 10 nanonewtons applied over a contact area of 1 nanometer squared. 10 nanonewtons is 10 times 10 to the minus 9 divided by 1 nanometer squared is going to be 10 to the minus 18, right? So we're talking about 10 to the 10 Newton per meter squared, which is basically 1 gigapascal. Does anyone know what the yield stress of most metals is? It's below a gigapascal. It's several hundred megapascal. So the point is, the notion that 10 nanonewtons of force is not much, doesn't seem much. It's 10 to the minus 8 newtons. But you're applying it in a very small area where hundreds of atoms, very high stress. And so you want to know if you're actually plastically deforming the sample. Are you causing irreversible damage to the sample? These are important things, especially if you do a biological sample. So the notion, and so here's the point. When you do tapping mode is great. Everybody uses tapping mode for imaging, but nobody knows what force you apply in tapping mode, because in tapping mode, you don't measure force directly. This is the problem. So the first effort at trying to get some idea of what force you apply is, let's try to find the average force. Now remember, as a function of time, if time is along this axis, and this is the tip sample interaction force, for the most part in a cycle, there's no interaction force, and then when you tap on a sample, there's this little pulse-like shape we talked about, which can be slightly asymmetric due to the dissipative interactions, right? So at first, what we would ideally like to know is what's the maximum force you're applying during an oscillation cycle, because the force changes like this, right? That's going to be hard to do. We'll talk about that a little bit. But even before that, it'll be useful to know what's the average value of this interaction force with the sample. That gives us a feeling for whether we're tapping too hard or not. So this was a nice derivation that was done in this paper by Alvaro San Paulo and Ricardo Garcia. And basically, it uses the same equation that we derived in the previous page, okay? If you look at the expression for omega effective squared from the previous page, it involves the varial, okay? Now, the varial is shown in the integral out here, is integral a cosine omega t times FTS, okay? That's the varial. Now, what they noticed is, look, this interaction force, right, occurs at the bottom of the swing, right? It happens at the bottom. At the bottom of the swing, what is the tip position? So the tip position is doing this. At the bottom, it's interacting. What's the rough value of the tip position during the interaction? It's negative a, right? It's most of the interaction is happening at the bottom of the thing. So while we can do this whole integral, the truth is the interaction forces are non-zero only when the tip position is at the very bottom. A very simple thing. So you can replace, so the whole integral can simply be replaced by taking a, so take a out and make cosine omega t minus phi equal to negative 1. Because that's when it's non-zero, the interaction force. So this integral, while it's done over 0 to 2 pi, for the most part, it's 0 because the interaction force is 0. But when the interaction force is non-zero, that happens when cosine omega t minus phi is nearly negative 1 at the bottom of a swing. So let's make that approximation. That's why there's a little approximation sign. And you just replace the cosine omega t minus phi term by minus 1, because that's the only thing. That's when the interaction is non-zero. And so then, what you're left with is simply this integral 0 to 2 pi over omega of f dt, right? Which is connected to the average force over the sample. So you get this expression for average force over the sample in equation 2. Of course, you have to remember this is valid only when the interaction happens only at the very bottom of a swing when the cosine is nearly negative 1 at the very bottom. So using that approximation, you can just go through the steps, equation 3 and 4, and you come up with this notion of what is the average tip sample interaction force during an oscillation cycle. It's given by this very simple expression, Ka over 2q square root 1 minus a over a0 squared. A0 is what we call the initial amplitude, is the amplitude at which you're driving before it interacts with the sample. A is the set point amplitude, is the amplitude at which you're imaging the sample, right? And that's it. So here you have a very nice expression for the average tip sample interaction force over the sample. there's something very surprising about this expression, in that it does not depend on the local material properties. It just depends on the operating conditions. You choose your cantilever, you choose your free amplitude, you choose your set point amplitude, and that decides your average force on the sample. All right, so this is a surprising result. And it's surprising because, remember, we talked about the fact that really the tip sample interaction force as a function of time is like a little pulse. You know, it's non-zero for most part, and then when you tap on a sample, it's a pulse. What this is saying is very interesting. What this is saying is that this interaction force is a pulse. It has a certain contact time with the sample, and it has a certain height, that there's a peak force. There's a height of this peak force, right? So this interaction force is like this. It's like a little mountain, right, in time. And it has a certain base and it has a certain height. What this is saying is, when you're in a soft sample, when you're tapping on a soft part of your sample, the contact time increases, the base of the mountain increases, but the height of the mountain decreases. So when you're tapping on a soft sample, you apply softer, less forces. Height decreases, but the contact time increases. When you're tapping on a hard sample, contact time decreases, but height increases. You apply larger forces. In a manner that, at least to first approximation, the area remains the same, so that the mean value does not depend on the local forces, local properties. Okay, very, very important, very, very critically important result. In fact, I encourage you to use this formula to get a feeling for what's the average force you're applying on your sample. Okay, and hopefully you get answers more like less than 1 nanonewton as average force. Okay, good. Very simple things you can do just with plain analytical approaches, integrating sines and cosines through. Very nice stuff. Okay. The other advantage of this is that most AFM systems allow you to measure the average force. Remember, as I said, in tapping mode AFM, what you do not measure is the real tip sample interaction force, how high, what the maximum force is, and all that. But this quantity, average force, is possible to measure, because in an AFM system, you can actually measure the average deflection of the cantilever. Average bending deflection of the cantilever is times the spring constant gives you the average force. So this is important for two reasons: that the average force can actually be measured. It's an observable in an AFM scan, and I encourage you to try and do it. You have to figure out what channel to get the mean deflection times stiffness gives you the mean force. One more other important thing to tell you. Remember when we talked about the attractive repulsive regimes of imaging in tapping mode? I hope you remember the definition of attractive repulsive when it comes to tapping mode. In tapping mode, when we refer to attractive and repulsive regimes, we refer to oscillation regimes where the net interaction force is repulsive or the net interaction force is attractive, respectively. Okay? The net interaction force is repulsive, if you think about it, when the average interaction force is repulsive, because the average interaction force is net interaction force divided by time period. So if the net interaction force is positive, the average interaction force is positive, the net interaction force is negative, the average is negative. Okay? Which means that in addition to using the phase, we talked of how you can use phase to judge if you're jumping between attractive repulsive states. You can also use the average force, which you measure in an experiment, as a way to tell if you're in the net attractive or repulsive states. Again, this is something nobody does today. Let's, as a group of people in Purdue AFM people, let's make a compact and move forward and try to map the average forces over sample also to confirm if you're indeed in the net attractive or net repulsive state. Why not try that? Nobody does it, but it's possible to do it.